I'm promised that Zoom will not have any problems, even though we have the wireless connectivity and all that stuff. We'll see. So we are going to talk about chapter 3 from the textbook. I would strongly recommend that if you haven't gotten the textbook, just go ahead and buy it, or go ahead get an ebook. Ebook is available for I think $40. Huh? Free? I don't. Man, you're awesome. So yeah, I don't know how he got book for free, but it's available for free. Okay. So what you can do is, as we go through the material, please try to review the material, and I will try to explain the theory, and I will also try to explain the practical implementations of the theory, because there is no fun in the robotics class without programming robots. One thing I just want to tell you, a student asked me a question. They want the full Mambo. I mean, full Mambo means Mambo with the cannon, with the gripper, and all the whole thing with the fly pad. That is also available, but that is available on Amazon.com, and unfortunately, it is $199. So if you want the Mambo with cannon, Mambo with grabber, Mambo with fly pad, that is available. So just take a look. And if you get to the point that you want to play with some of those simulating blocks, then I would be happy to give you a grabber. I would be happy to give you a cannon, and you can program your Mambo so that the Mambo can shoot cannonballs, or Mambo can perform the formation flight. It can do pick and place. Okay, so let's start with today's class. The key question that I want to talk about in today's class is, when do we design, or when we select a multi-copter, what type of airframe do we choose? As a designer, we have choice. We can choose an airframe with 4 rotors. We can choose an airframe with 2 rotors, which are mounted opposite to each other, which is called the coaxial helicopter. We could use the helicopter, or we could use a multi-rotor with 6, 8, or as big as 12 rotors. The problem with that is there are scaling laws. So which means you cannot just keep on adding motors and expect that aircraft to perform better, superior. You gain somewhere, you lose somewhere. So where do we gain and where do we lose? So in this lesson, I'm going to talk about the configuration design. I'm going to talk about the structural design, and I would give you some hints on something called as the dimensional analysis. And dimensional analysis is the key that allows you to build the small scale models of the large scale systems and come up with some meaningful interpretations of the data. Here is a very simple example. If you think about Boeing 747, they don't build hundreds of Boeing 747 and test them. What they do is they make the small models of Boeing 747, test them in the wind tunnel, test them in a different environment. And from those small scale models, they interpret or interpolate the result to the long big scale model. This scaling would work as long as 3 fundamental similarities are maintained. And those similarities are geometric similarity, kinematic similarity, and dynamic similarity. And you will see the Reynolds number, Froude's number, all those concepts, when we talk about it, those numbers, those are dimensionless numbers. They ensure that whatever result you get from this small scale model, you would get similar result from the large scale model, and it can be scaled up. So we will talk about it, but today, later in the class, there will be something like Froude's number, something called as the Reynolds number, and then there will be some proportions. So those are used for dimensional analysis. So fuselage configuration. So how do you mount rotors? Please understand the quadcopters means you need to have 4 rotors. Out of those 4 rotors, 2 rotors should rotate clockwise, 2 rotors should rotate counterclockwise so that the action torque is cancelled out by the reaction torque. Ideally, there is no rule. So if somebody says, I want this rotor to rotate clockwise, I want this rotor to rotate clockwise, I want this rotor to rotate counterclockwise, I want this rotor to rotate counterclockwise. Moment wise, this is fine. It still is okay. But unfortunately, this will not have the complete articulation. What it means is, oh, they are all clockwise. Yeah, you're right. Yeah. Oh, I was looking for one from top, one from bottom. Anyway, so yeah, so it can be like this. Still, the moment would cancel, but typically what we do is we have opposite. So if this is clockwise, this is going to be counterclockwise. So this is so basically you would have one pair going clockwise and one pair going counterclockwise. So if this is going clockwise, this is going to go counterclockwise, this is going to go counterclockwise. So that is the way. This is called as the plus configuration. You could also have the X configuration. And depending upon the design that you want, depending upon the agility that you want, you would have different types of configuration. So if you think about, let me ask you a quick question. Tello, what type of configuration does Tello have? X. Mambo, what type of configuration does Mambo have? X. So X configuration is fairly a famous configuration. And the reason that X configuration is famous because something called as maneuverability. So it's very easy to maneuver. Please understand, quadcopters are inherently unstable. So which means unless you have some sort of active control system, that is the closed loop controlling the speeds of the motor, if you just put 4 motors together, run them at even constant speed, you would think, hey, that quadcopter should take off. No, it will not. Basically, you have a control system that is actually monitoring the roll, pitch, yaw, and then adjusting, making those changes to the rotor speeds, fine changes to the rotor speed, so that that quadcopter is stable. If you haven't played with Tello, I would strongly encourage you, once you get the drone, just charge the drone and try to do the flips, 4D flips, 8D flips, and you will realize that drone will take off, do a flip, and stabilize. That is a very, very complex maneuver. To achieve that type of maneuver on a small footprint drone and still make it stable, it's quite an achievement, because there is the dynamics of that flip. It needs to control that in real time. So I would encourage you to play with that drone, and then you will realize that not only that drone is very well designed in terms of its mechanical hardware, and we'll see what features are implemented in the drone, but from control system point of view, that is also a fantastic design that allows that makes that drone very stable. So next thing is what type of fuselage you want, and you can have a fuselage like a rectangular fuselage that is shown on the right hand side, or you could just have the booms crossing each other. The problem with that type of fuselage is basically it adds to the weight, and quadcopters are basically very inefficient for flying, because for hovering you actually have to supply electricity, or you have to supply the battery voltage and current. So basically if you have a fuselage that is aerodynamically not efficient, you are going to spend a lot of energy just to maintain a stable hover. So what we do is we try to go with some sort of X type of configuration or plus type of configuration, or we can go up to some sort of coaxial type of configuration. Now, please try to understand. It's not like if you take a quadcopter, add maybe two more arms, make it a hexcopter, add two more, make it octocopter. The efficiency is going to scale up accordingly. No, it doesn't happen that way. That is where the scaling laws come in the picture. You cannot just take a quadcopter, make it bigger, and expect if a small quadcopter can lift, say, 2 pounds, a twice big quadcopter should be able to lift 4 pounds. No, it doesn't happen that way. And I will show you towards the end of the class, there is a fantastic tool that this author and his students have developed that will allow you to perform these type of design of experiments. And so one thing that you can think about is, as designers, they are coming up with this new configurations, and we will go through some of those configurations. Right now, we have a project and Borna is working on it. So if you talk to Borna today, ask him to show you the coaxial motor design. So the coaxial motor design, he and his capstone team has actually built a coaxial rotor. But flying those, it's a 16 inches prop. It's dangerous. It will like cut your fingers. So that's why we built a cage, and that whole thing is sitting in the cage. So you can talk to Borna and he will show you the prop system and the whole assembly for the coaxial rotor system that he has built. So here is the issue. If you have a coaxial system, the advantage is basically you have one rotor rotating clockwise, the other rotor rotating counterclockwise. So you don't need some mechanism to counterbalance torque. But here is the problem. You have the issue with the rotor downwash, which means the airflow that is coming from the top rotor hits the airflow that is going on the bottom rotor. So the efficiency is reduced. That's why there needs to be certain distance between those two motors, basically between those two props, so that you actually minimize the effect because of the downwash. And that's what they say, that this H divided by RP is the radius of prop, has to be greater than 0.357. They did experiments and they found out these this sort of the ratio. And now, so nowadays you will see sort of exotic types of designs. When I started working in the areas of UAV squads, I always used to look at the aircraft or quadcopters where the motors were perpendicular to the booms. So the boom is a flat horizontal airframe, and motor perpendicular to the boom, motor perpendicular to the airframe. Nowadays, you have Sci-Field LVL1. This is actually a hexcopter. You would notice this hexcopter, the rotors are not perpendicular, but they are at an angle. Rotors are not perpendicular. The rotors are at an angle. Can someone tell me why? Basically, this is no longer, okay, once again, initial the problem was, if you have the quadcopter with vertical props, vertical motors, it cannot go like this. If it has to go left, it needs to tilt and go. If it needs to go forward, it needs to tilt and go. With this, here you have a component of thrust in the X and Y direction. So you can actually, it becomes, you overcome that under actuation by this. Where is the problem? The problem is you need a superior control system so that to compensate for those thrust vectors, which means you don't want when the multi-rotor, when it is hovering, you don't want those thrust vectors, the component of thrust vectors to go towards left, right, front, or back. So you need a control system that would compensate by changing the speeds. So that under articulation has been compensated sophisticated control system. Now, and depending upon the designs that you use, and nowadays the drones are used for, say, for photogrammetry. I don't know if you know what photogrammetry is. Basically, drone will fly, take picture, and then get those pictures, stitch them together, and give you something like a Google view. And it will actually do it so nicely that you can select the points, and it will tell you the distances. So basically, what you do is you will fly multiple drones, and then those two drones will stream the images. Those images will get stitched, and then the person who is sitting at the ground station can actually click a point, click second point, and actually find out the distance between those 2 points. And that tool is very, very useful. I have seen the application there that is used for mapping. So if you have a cave, rather than sending someone inside, you send the drones. If you have tunnels, like the tunnels that we have on the Arizona-Mexico border that are used for smuggling. So what they do is, instead of someone going in, then they actually do it. They send the drones. Then basically shipyards. So if you want to monitor the ship, the surface for corrosion, you basically send the drones. If you want to monitor crops, you send the drones. Basically, you want to spray the pesticide, send the drones. So there are a lot of applications, the drone related applications that are coming up. Now, again, we just talked about it. Again, this is the DJI drone. So the application of DJI drone is for camera stabilization. So there are different techniques for stabilizing camera. One is digital stabilization, which means what you do is you have an IMU inside, and that IMU, based on the orientation, vibration, it will run in built-in filter that will take out the jitter. So basically that is the gimbal-less camera. Or you could have a gimbal, and basically you would have motors that would stabilize the camera in a particular location. So now if you look at the props, you will notice props could be mounted upwards, prop could be mounted downwards. Depending upon what your application is, there are advantages and disadvantages. We will talk about this not in today's class, but later. So if you think about the drone has sensors. So for example, the Telo drone or the Mambo drone, it has a barometer. And if you think about it, if you have the props on the top, that all the downwash makes that output of the sensor very noisy. And that's why, depending upon what type of application you need, what type of performance you need, you would select a particular configuration. By the way, DJI Phantom is a very famous drone. I don't know if you have used it or if you have flown it. It's a very nice drone to fly. So now there is another key consideration on how do you actually design the configuration, like how many props to use, how many what should be the radius of the props. Please understand, when you are going to do the drone design, everything needs to be matched perfectly, which means the airframe size needs to be matched with the prop size. Prop size should be matched with the motors. The motors should be matched with the ESCs. ESCs should be matched with the flight control system, stabilizer system, and then you will select the batteries. And all these, there are trade-offs that you will have to go through before finally you finalize the configuration. So airframe radius and the maximum prop radius, that relationship is given by the angle theta, which is the angle between the two arms. And then the reason for choosing either a quadcopter or hexcopter depends upon sort of balancing the requirements. And I'll go to that website later. There is an online tool which is called rFly Eval. you will see what it does. It will actually give you the database, and you can perform the design of experiments and select the basic frame, ESC, battery, and it will give you theoretical hovering performance, theoretical application, and so on. So again, there is additional information about if you want to find out what should be the Rmax. Rmax is usually about 1.5 to 1.25 times Rp, which is the prop radius. And then again, these relationships, they come from the experiments and CFD analysis. Now, another important aspect, and this is where I was talking about the dimensional similarity, kinematic similarity, and the geometric or the dynamic similarity, kinematic similarity, and the geometric similarity, is please try to understand. TP is the thrust that is generated by prop. Thrust generated by the prop is given by 1 divided by 2 pi square. It's a constant. CT, which is the coefficient of thrust, multiplied by rho, which is the density of air, multiplied by omega, which is angular speed, omega square, and multiplied by the radius of prop to the power 4. So the thrust given by the prop is Rp to the power 4 proportional to omega square. MP is the torque, and the torque is given by 1 divided by 2 pi square. Cm is the coefficient of movement. Rho is the density of air. Omega square, but note 2 Rp to the power 5. So these are the scaling laws. What does it tell me? It tells me that thrust is proportional to the Rp to the power 4, and the moment or the torque is proportional to Rp to the power 5. And those allow us to find out the numbers of proportionality between the overall thrust and the thrust generated from the prop. And then you will realize that M is the mass. Mass is nothing but density multiplied by volume. Density is constant. Volume is length multiplied, it's length, width, height. So it is, that's why mass is proportional to R cube. J, which is the mass moment of inertia. Mass moment of inertia is mass multiplied by the radius of gyration square. Mass is proportional to radius cube, multiplied by radius of gyration square. So J is proportional to R to the power 5. So please understand what is happening here. I'll try to give you just intuitive feel for what is happening. Geometry is nothing but lengths. You agree with me? So you have an aircraft which has maybe small boom, and you have another aircraft which has a large boom. What you want to do is you want to come up with some sort of quantitative assessment. This boom is maybe 12 inches. This boom is maybe 12 feet. What does it mean? So how would the power scale up? How would the thrust scale up? So for that, you will have to use these relationships. You will understand that the dynamical effects, which is mass, moment of inertia, they would scale R to the power cube and R to the power 5. On the other hand, the thrust that is generated would scale R to the power 4, and the moment or the torque would scale R to the power 5. And then finally, when you combine all this, I don't know if you have studied this, there is something called as Buckingham pi theorem, which is used for dimensional analysis. So what you do is, basically you find out the dimensional numbers. And then if you say that this dimensional number, this dimensionless number for this airframe, if this is same as this big airframe, everything would scale up accordingly. I give you a very simple example. Everyone knows what a BMI is, right? BMI is the ratio of, I think, height divided by weight. Everyone's weight or weight divided by height. right? So BMI is weight divided by height. Everyone's BMI is different because everyone's height and weight is going to be different. But that gives you a number. You would say if someone's BMI is between, say, 20 to 25, that's normal. 25 to 30, that is overweight. Or if the BMI is more than 30, that person is obese. So what you have is you have two parameters, seemingly unrelated. You found a ratio and then you got a number. And that number tells you whether someone is overweight or not. Same thing happens in the dimensional analysis. You have these seemingly unrelated quantities, but you combine them together, get some dimensionless numbers, and if you say the Reynolds number for this flow and Reynolds number for this flow is same, it means whatever measurements I make here, same measurements would be replicated here. If I would say another number, say Froude's number. Froude's number for this airframe or this top is same as the Froude's number for this Boeing 747. Whatever result I get over here, those results can be used for Boeing 747. That is basically the purpose of dimensional analysis. But the key here is, as the size goes up, the maneuverability goes down. That's why many a times it's easier, rather than building one big aircraft, you can have 2 or 3 aircraft performing a task collaboratively. That's why this swarming is so popular, because many a times you can't just make the things bigger and expect the system to perform the way it performed earlier. You lose on efficiency. So what you do is, instead of making the aircraft 2 times bigger, what you do is, instead of using 1 aircraft, you use 2 aircraft, but then you maneuver them in some sort of formation. That is where the swarming comes in the picture. Now, next thing is, center of gravity of the aircraft is super duper important, because depending upon where the center of gravity is, the aircraft would be stable or unstable. I give you a very simple example. So if you are walking, you would fall down if your center of gravity is outside the span of your legs. In other words, if my center of gravity is outside the span, then I would fall down. In other words, if CG goes outside certain range where the internal moment, rather than stabilizing, destabilizes, the thing falls down. And that's exactly what happens in the case of aircraft. That's exactly what happens in the case of quadcopters. So let me give an example. Imagine we designed this fantastic quadcopter, but unfortunately, the center of gravity of the quadcopter is below. The center of gravity of the quadcopter is below. There is an air gust. Because of the air gust, the quadcopter goes like this. Then please understand, there is drag force which is going towards right-hand side. And as you can see that you have that the drag torque that is acting around the center of gravity is clockwise, then what would happen is basically, even so, if you think about it, the aircraft initially was in a level flight. The wind gust came. Because of wind gust, aircraft tilted, and because of the drag, it gave a moment that added to the instability. So basically, the aircraft or the quadcopter would flip. But on the other hand, if your center of gravity is above, even though you have the flight direction is in this direction, you have the wind gust, and then you will realize that the moment given by the drag is going to counteract, and that would bring the aircraft to a stable position. Quadcopters are not inherently stable, so you need a flight control system. And many a times, by adjusting the location of the CG, you can reduce. Yeah, question? Did I say that wrong? Okay, I can't see. Okay, yeah, the flight direction is on towards left. Okay, yeah. So I made a mistake there, but please try to understand that CG is okay. CG is under the prop disk, then the drag torque, and top one is CG under the disk. Right? Oh yeah, the top part is going to make the aircraft stabilize, and the bottom part is going to make it unstable. Couldn't see. So anyway, you understood the idea, right? Any questions? Okay. So same thing, and you would observe similar thing in the ships. You would see similar thing when you are walking. So now in the quadcopters and aircrafts, there is always the issue, something called as the flutter. The flutter means when the eigenvalues become positive, the system becomes unstable. So basically, you want that system to be sort of a damped pendulum. But if your eigenvalues get positive real parts, then the system becomes unstable. And this is what it shows, that as the center of gravity changes, the real part, as the center of gravity changes, the real part of the eigenvalues, they changes. So as long as the real part of the eigenvalues is negative, the system is stable. I want you to track the blue line on the top. You would notice as the center of gravity increases, the height of the center of gravity increases, after some time, you would observe the real part of the eigenvalues become positive, and that is actually an instability. So you would want to avoid that. Now, it's not very intuitive, but please understand, when the seat assignment is done, they take this into account, because please understand, you have a cargo plane. Initially, you don't know how much of cargo is going to get loaded, or you do not know what would be the weight distribution of the passengers. But what they do is, when they assign seats, they take into account the age and possible weight distribution and assign the seats accordingly. Also, there is something called as the stability margin, which means for the aircraft, usually the CG is in the front so that the aircraft flies in a stable fashion. Now, the question here comes is whether stability is good or bad. On the other hand, if you look at the design for F-15, F-16, or fighter planes, those planes are designed to be unstable. Those are inherently unstable. Why? Because you want those planes to maneuver very quickly. If you have a stable aircraft, it's not going to maneuver very quickly. If you have an unstable aircraft, basically maneuvering is very easy. That's why the fighter planes are designed to be unstable, but then they have active control system that is actually controlling the behavior. Autopilot system adds the weight, and then basically the idea with the autopilot system is if you can install the autopilot system at the CG of the aircraft, that is the perfect position. If not, you get something called as the lever arm compensation, because in the autopilot system, you have accelerometer, you have gyros. Remember, rotational velocity of a 3D rigid body would be the same no matter wherever you take the center axis. But the translational velocity of the three-dimensional rigid body is going to be different depending upon where you have your axis. So you want to be very careful. You get something called as the lever arm effect. What it means is if you have this aircraft and this aircraft CG is over here, and then think about it like this starts spinning. So gyros would measure the same thing. So gyros is going to give you the angular rotation rate. But if you have an accelerometer that is located at the very end, the accelerations measured by that accelerometer would be the acceleration at the center of gravity plus the centripetal acceleration and tangential acceleration that will affect the measurement of the true acceleration. So there is this lever arm effect because the accelerometer is not mounted at the center, that you will have to compensate. Now, the good news is that if you were to play with autopilots like Peacock or APM, they have built-in calibration routine that would actually allow you to program those autopilots to compensate for this lever arc effect. Drags are something that we need to avoid. So there are 4 different types of drags. There is frictional drag, pressure drag, induced drag, and interference drag. So most important drag that we look at in quadcopters is the pressure drag, which is because of the pressure differential on the incoming side and on the outgoing side. So you want the body to be streamlined. That would minimize the pressure differential, that would minimize the drag. How many of you play golf? Have you seen that the golf balls, they have dimples? And the reason for those dimples is to minimize the drag. So remember that the golf balls are not smooth. They have dimples so that to minimize the drag. Then again, there are different configurations. I don't know if you have seen this. DHL played with parcel delivery, just like Amazon. So that's a DHL parcel copter. Then there is DJI Inspire, there is micro drone, X-Craft Ignition. And then when you try to design, you just have to make sure that your airframe, your props, your motor, everything is well matched. And sometimes what you do is you use computational fluid dynamics software to model this. Now, I'm not trained in CFD. So I used to be like, oh, wow, CFD is super duper difficult. But let me tell you, nowadays, there are cloud-based tools that would allow you to perform fantastic CFD analysis in minimal resources. So CFD usually takes, so when I was a student, graduate student, you couldn't perform computational fluid dynamics on the desktop. You would need a cluster or a supercomputer. Nowadays, what they do is they do something called the GPU type processing, like CUDAs and all. That's a fantastic field to get into because we are going to transition to that. I don't doubt it that after 3-4 years, everyone will have a supercomputer on the desktop. So basically, and GPUs are used for Bitcoin miners, by the way, if you don't know. So what they do is they actually download all these repetitive calculations onto graphic processing units, and then basically those get performed parallelly. They do massive parallelization. So if you are interested in drone design, some exposure to CFD software would be good. And there are free online cloud-based CFD softwares that would allow you to perform the computational fluid dynamics on different types of airframe, different types of props, different types of, you can actually do some type of wind tunnel, virtual wind tunnel testing using those softwares. Design principles. Now, design principles should be the airframe should be rigid, it should not bend, it should be able to sustain the loads, it should be able to actually aesthetically good, it should be able to perform the way we intend it to work. And then clearly you want to add some sort of damping elements. They could be some sort of isolators, they could be some sort of active vibration damping, but there are different types of dampings. Now, I don't know if you have seen this. Professor Zhang is actually working in the areas of foldable quadcopters, wherein the quadcopters fold. There is another area where the aircraft, they are foldable. The idea is you fold the aircraft in a direction in which it's not loaded when it's flying. I repeat, the aircraft can be folded in such a way that once you unfold it, it is strong in the direction all the forces are coming in. So there are different design principles that are used to design these foldable frames, foldable aircraft. If you are taking foldable robotics class, Professor Akas will talk a lot about the origami-based robots. And you can talk to him about designing a quadcopter, which is based on the foldable robotic principles. So anti-vibration design, you can have motor mounts, you can have rubber isolators. If you look at the Mambos or if you look at the Talos, you will see that the motors, they are mounted in the rubber isolators. So that is to minimize the vibration from the motor. And then props are the biggest source of vibration. And basically what you do is you basically use different isolator designs, different techniques to minimize the vibration signature. Typically, when you have an aircraft, when you do some sort of wind tunnel testing, you get a vibration signature. You kind of characterize the overall vibration and then use some type of filtering to minimize those vibrations so that the navigation data that you get from the navigation computer or IMU is meaningful. There are different isolator techniques, all the way from some fed pads, some rubber bushings, all the way to the elastic bands for small aircrafts. For large aircrafts, there are dampers. And then the important noise characteristics or noise generated from the aircraft is because of the prop, and you can actually sweep the blade, or you can actually increase the angle of the blade and use these different noise reduction techniques. You can make the aircraft aerodynamically more. So basically, you can use NVH type of analysis, noise, vibration, and harshness type of analysis, and try to streamline the aircraft design, streamline the body that would minimize these sources of vibration. If you look at the different noises, you would see there is a tone noise, there is a broadband noise which is across the board, and then depending upon where that noise is generated, even the ESCs would generate, because of the switching, ESC would generate noise. So what you do is basically you identify those sources and then either use the hardware or software tools to minimize those noises. In short, there are different design principles, and as a designer, you have a lot of latitude on what type of design principles to use, but these are the basic design principles that are used in design of quadcopters and octocopters. So with this, what I'm going to do is, again, the slides came from the author. Now what I want to do is I'm going to change my screen and I'm going to show you a couple of things on using my MATLAB. So if you have MATLAB, I want you to go to MATLAB and type ASB quadcopter start. I'll show you the entire screen. ASB quadcopter start. If it doesn't start, it means you don't have the libraries that we need, and you will have to install the Parrot Mambo library, and you will have to install the UAV toolbox. Now, we are going to play with this a lot, but I just want you to understand, what do you see here? This is the Parrot Mambo. So this is the dynamical model and the control model for Parrot Mambo. What you can do is you can, and actually this is the instrument panel for the Parrot Mambo. So you can actually get the data from Parrot, that Mambo, and basically see how that quadcopter is behaving. So are you with me, everyone here? ASB quadcopter. ASB quadcopter start. it's a big project file. So it will actually load all the files, and then it will actually open the simulator. Got it? Is it opening? Not opening? Okay. It will take some time because it has to load the entire project. Then you would see the flight simulation model for this is the whole flight control simulation code inside the Mambo. Now, what I want you to see, we are not going to play with this model, Simulink model today, but look here, you can actually manipulate the sensors. So you can actually take the feed forward sensors, or you can do feedback. So you can actually see the effect of disturbance, effect of external environment on the actual simulation. I want you to play with this. Please understand, here is what we are going to do. We are going to play or change these parameters. We are going to observe the parrot Mambo inside the virtual environment. Take this code and flash it on the actual parrot Mambo and see if the actual parrot Mambo, when it is flying, is it going to replicate what we see in the simulation environment. You will also change the noise parameters. You will also change the thermometer gains. You will also change the PID gains. And then you will see that the aircraft that is actually flying in a stable hover, once you change the PID control gains, it actually becomes super unstable. So please make sure that you are able to load this. And then this is the flight control system. Parrot Mambo has optical flow vision based sensor from the downward facing camera. It also has the ultrasonic sensor that gives the height information. It also has the barometric sensor. So you have an image processing system that is going to capture the data, convert this into the format, and then actually pass it on to the flight control system. And then you can see that there is optical flow, there is position, there is sensor data, and then basically you do the sensor the estimates, and then there is filtering. So you can see here there is acceleration, gyro data, ultrasound, pressure, battery, all that stuff that goes on to the here. And then later, what you can do is there are two types of airframes. One is a non-linear airframe, because Parrot Mambo is essentially a non-linear system. There's a non-linear airframe and there's a linear airframe. So you can change the airframe that you can use, and you would see how good your simulation is, how good your simulation is matching with the actual performance. Where do we look for ASB quadcopter start? Props to you, Professor. Okay. You don't look, you just type it in command window. And if you have the appropriate toolboxes installed, it should open. If your toolboxes are not installed, then the toolboxes that you need for this system, they are basically Vision toolbox, Parrot Simulink toolbox, and then Simulink 3D visualizer toolbox. Yeah, what? So just start running. I mean, see, then you'll see. Okay, then what you can do is, once you manipulate, you can generate the flight code. You can select the target. We are using Mambo, so you can actually set the Mambo model, and then you can do the trajectory planning, and you can implement different trajectory planning algorithms. So please try to play with this model a little bit. And then I would actually talk to you about trimming, linearization, and all that stuff as we go forward. Next thing which I want to talk about is real quick. How do we question? Any question on? Yes. Yeah, list of libraries I need to install. Actually, I don't remember what libraries I use. I actually install all the libraries. Oh yeah, she has a list. Good. You can email it to me. I'll upload that to Canvas. Okay. See, I'm lazy. Oh yeah, here. Oh yeah. Yeah, here. Somebody. Okay, Coursera. Please understand, I do not want you to pay for Coursera. The courses should be audited, which means you should be able to do the courses for free. The only issue would happen is you won't be able to turn in your homeworks and assignments, but you won't turn it into Coursera. You will turn it into Canvas. Everyone understood this? Yeah.
Do you want us to do the quizzes
and homeworks?
All of it?
Yes.
Okay.
And take a snapshot. And if you want to maximize your return, what you can do is at the end of the semester, you can take a 7 days free trial of Coursera, submit everything, and get the certificate from Coursera and put it on your LinkedIn. That's what Taufik did. He got 3 courses. I mean, 3 certificates, right? Yeah. What, 4, right? 3. So they will be super helpful because I would be honest with you. I know students who got jobs because of those Coursera courses. They put those courses, certificate on the LinkedIn, and they got jobs in the robotics field. So I would strongly recommend that after finishing, don't purchase the Coursera subscription now. Get everything, make all the homeworks, do all the homeworks, arrange them neatly. At the end of the semester, just enroll for that 7 days trial, upload everything, get the certificates, and then cancel the trial. Any question? Yeah.
So for the quizzes, you want us to write it in a Word document?
No, you will do the MATLAB code and upload the MATLAB scripts, everything onto the Canvas.
What about like
The quizzes, I think the quizzes you enter, they take the snapshot and upload. Take the picture. You won't type it in the Word, just enter there, take the picture, and upload in Canvas. Right, Tatvik? Any question about Coursera classes? Yeah.
So just to clarify what you just said, we complete the quizzes, but we don't submit them. Just take a screenshot of the quiz answers.
So you will there are 2 things. There are some MATLAB assignments. You can't take and there are some online fill in the blanks, or I think what is just typing some answers, something like that. Multiple choice. Once you do that, take a snapshot and upload. But for MATLAB assignments, you finish the MATLAB assignments and upload your code into Canvas.
Thank you.
You have 4 weeks to finish. It's a 4-week class. And if you do that, so I will actually just take you for a second to Coursera. If you go to, Coursera. So if you go here, it's a Coursera course. and there are 4 weeks. This is week 1, week 2, week 3, and week 4. So this will give you a very basic understanding of the quadcopter dynamics, some MATLAB code, some hands-on experience with PID that would help us to do the low-level programming on Tello and on Mambo. So very good course. I have finished it. So, and Satwik has finished 3 of those. Teja finished. Surya also finished. So if you work on it, you should be able to get that done in over 2 or 3 weekends. I don't see a big issue with that. Any questions here?
So do we need to even turn in the week, this week 1, week 2, week 3 MATLAB scripts where there are simulations of the quadcopter?
Yes, simulation quadcopters. So that similar. So we will be grading those. Coursera won't grade it. We'll grade it. Yeah. If you upload the certificate, you have to pay, right? Why do you want to pay? Oh, you can, instead of that, yes, instead of that, you can upload the certificates. Okay, next thing, drone blocks. Go to drone blocks. Somebody asked me, where is this drone block? So go to drone blocks and make sure you will have access to these 20 lessons. Some of these lessons are super duper simple. So for example, troubleshooting Tello, intro to Tello, drone programming, Tello block coding. They are just for high school kids. But it's good to do this. Please see how you would use the drone block simulator. Then how to do Tello EDU programming using drone blocks. Advanced Tello programming with drone blocks. This is the function. This is using blocky. It's again drag and drop type of environment, but I want you to see that the blocky code can be converted into a conventional Python or Java code. So that is super important. Then what you can do is, there is some fun exercise. The important part is you can actually do Python coding. So this will teach you how to do very basic Python programming. That is all you need. If you know MATLAB, Python is simple. So it's basically transferable knowledge. So you do Python. There are some examples on Python. Then you have access to the low-level imaging from Tello. So how would you access the camera? Then the important part, OpenCV, is how would you interface in OpenCV, Python, and how do you do some little bit of sort of toy problems. Then there is Python 3, OpenCV, and RUCO markers. That is also interesting. You should do. And then you should do the Node.js or JavaScript programming and Node-RED programming. So once you do all this, you would be fairly conversant with the basic control of Tello using Python or maybe some other higher level language. Yes.
So if we're all logging in with that same
Yes.
log,
Yes.
how do we show you?
Oh, just like you take a picture.
But it tracks everyone's log.
Yes. Every time you do the login, it will track. So okay.
When I
please-
logged in, there was like 3 things.
Yeah. So please follow the honor code. I understand your question. So basically, like, oh, I have somebody else has done it. Can I take a picture? If you want to, you can, but you won't learn. So my recommendation to you is just follow the honor code, do those labs. But I would know that whether you have done those or not, because there are 8 intense Tello labs that are coming your way. So if you have done these, then that would be straightforward. So please do these. That's why there are just 5 points for completion of it. But do these. Any questions from my online students? If you want to go for the UAV flight pilot license, there is a course there too that actually would help you train for the FAA certification exam. So with that, I'm gonna stop here, and then I would be happy to answer any questions you may have.